Hello. Today I want to make a quick update about my CNC project. I'm at the end of gathering parts for the mechanics. I'm missing only pulleys, basically from mechanics point of view, and also spindle parts. So what I have here for screws, I have 32 millimeters, 5 millimeters pitch screws. They are highest grade screws that I can get. These are also given. Everything is here is from Given. So I have a 32 millimeters nuts. They are basically many ball bearings that's circulating inside this nut, and it is very firm. So also I have a two on each side. I made a mistake. I have first bearings, so that's not ideal because of thermal expansion and other things. So what I'm thinking to do is to converting one of the side to the simple radial bearings, or I will machine two inserts inside plastic bushings, so it will act as a very stiff spring. So I will have a two compliant parts inside the structure. So this should be a very stiff design. Okay, so for the servos, I have four clear path servos. So will be for the gantry movement. This is for X and Z. This will be for the rotational axis. It will be for A. So basically I will have 4 axes. And for 4 axes I have this very nice harmonic gear. Basically U-turning harmonic generator, and there is a flex plate that is spinning inside. So reduction of the spinning is 1 to 200. So with 5 Newton meters I'm getting basically 200 times more torque, but it has some resistance, so it will generate very lot of losses. But one thing is good about this harmonic gear, that is very stiff in the rotational direction, because at any given time there is two places where teeth are engaged, and there is no backlash, nothing. It's very stiff. Basically, it's the best 4 axis you can get, and it will be coupled to this servo. So this is basically inserted in here like this, and this will generate a wave generator. This will turn wave generator. And this is the stator, and this will be going to the chuck. So for chuck I have a this is the chuck. Let's zoom out. Okay, so this is the chuck. This is a self-centering chuck. So basically there is a one adjustment screw. Basically it clamps the device, not device, but what is good for why I choose 4, because if I want to have a plate, these surfaces will be always clamping in the center. So this is why I choose a 4-jaw chuck, and this is very nice. I tested it. It's very rigid. There is no play, at least right now, and I'm quite liking it. I don't know if I did mistake not buying a chuck with adjustment on each side, so it will be better for centering, but well, I'm still learning the stuff. So for bearings I have for linear guides I have these rails. These are 30 millimeter rails. Now they are very nice. This is a for Z. This one, it's very smooth and very stiff. It's for preload point of view, it's at medium preload. So there is a high, low, and medium. So I choose medium to have a stiffness high as I can get. And these are not any simple linear guides. They are roller guides. So what that means, there are 4 rows of roller elements. They are basically cylinders, so we are touching there's 2 surfaces at 90 degrees basically, and the roller is riding on them, so they are very large contact area, so they are extremely stiff. And this is what I'm using for Z and X. And for gantry movement, if you easily startle, please turn around now, because I have 35 millimeter roller block. So yeah, so I have more than 1 meter of rail, and this is the block. It's a bit on the big side, and this is what I don't know if I'm able to show it. Oh, not on this one. Let's go on. Let's go show on this one. Roller elements. So these are, you see, let's focus. Yeah, you see, we are roller elements. We are not balls like usual. So we are extremely stiff. So in theory, even rails and only rails are much stiffer than someone else CNC. And I'm still planning to use some heavy-duty aluminum profiles or something like that to construct the frame. So for now, what I'm missing is a pulleys for the servos. So servo will be coupled with a reduction ratio, and I want to have reduction ratio so that one step it will be equal to 0.5 microns. So this is very low, but I just want to have this very nice number. For that I need 75 and 48 tooth pulleys. Now I need GT2 pulleys, they are power grip, and for the size I need, I can't find them, or they are very expensive. So if someone knows how to find them, that would be very nice. So yeah, so this is my system. I will show you the rails. They are extremely heavy, and they are very large. This is how it looks. So this is for gantry movement. So they are very nice and very heavy and very big and very strong. So the system should be extremely rigid. Okay. For servos power, I think I will have 2 power supplies. For fourth gear and these 2 smaller clear path servos, I will use like 1 kilowatt. So this is a nearly 100 volts power supply. It's 1 kilowatt. So I don't know if I need more power or not. If I need, I will buy 2 of them. So this servo will be high, will have highest loads, and this servo will have lower loads. I was thinking of balancing Z movements, so it will be neutral. So basically, if I don't install the screw with all my motors, with all my tools, it should be hanging inside the middle, basically like a lift. Same idea. You balance the load. You balance it with spring or something like that. So yeah. So this is my gantry rail guide and bearing basically, and I have two on each side. So one next to the other. So it should be extremely stiff. Okay. So what about spindle? For spindle, I want to have a automatic tool changer, but that's very hard to do. I don't know, and it's very expensive. So, at least for the spindle motor, I have Revolt RV120 Pro motor. It's very powerful motor. It's 66 kV. So, what I will have, I have 100 volts pure sinus driver. With an encoder feedback. Encoder will have 1 to 2000 counts per rotation, so I will have very good tracking on the motor. So in theory, I will able to line up my I don't know how they call line up my spindle tool with a case. So this is one of the requirements if I want to make automatic tool change in the software. So basically my spindle is nothing more than servo, very high power servo with some precision. So I don't know if it will be possible like to make a thread. It will be synchronized with all of my system. Okay, so this is for spindle. My controller. So for controller, it's nothing new. I will use Ethernet smooth stepper, but I will also going to use a very huge Altera. Basically, where is it? I can't find. So basically, I will use a Altera, Altera Max 10, highest Altera, highest performance Altera. It will be coupled with 4 ARM Cortex M4 processors, and they will be coupled with encoders. These are 1 micrometer encoders. You already know about them. So basically, this is a differential encoder with a hole. So my zeroing will be done with magnetic encoders. So basically, Ethernet smooth stepper will be generating pulses. It will go to Altera quadrature decoder, and for each axis I will have one of these encoders, and I have ARM Cortex M4 processor that will track how many steps I get from the Ethernet smooth stepper and how many pulses I actually went with my servo system, and it will try to match those numbers. In theory, I will have at least around, if I exclude backlash from the encoder, that is 1 micron, should have at least 2 micron resolution, at least electrical resolution, how I can't position my system. So in theory, I will be able to position electrically, basically from processor point of view, within 2 microns. But of course, mechanics will be not that precise, and I mean, angles are not exact 90 degrees and we're to each other. So in reality, I will not get this precision, but at least from electrical point of view, I will. So that's very nice capability. Also, I will do software limit switching. So basically, anytime I move, I will have an exact position where my machine is, and it will be running inside the processors for each axis. So I can limit the movement, and I will know that I'm reaching the limit of my machine. And if my processor will go to the south, whereas of course hardware limit switches, they are opto interrupters, and they will cut power or do something like that. So, and another thing, for each processor will have a RAM memory. That's basically not non-volatile memory that can be read and write millions of cycles without any degradation. So at any step, I will write the correct position to the FRAM, and at a power loss or any other device, event, processor will know where my axes are. So that's also very nice to have. So yeah, idea is and also I'll have a 4th ARM Cortex M4 processor that will be interfaced to the computer, and it will have all the diagnostic information and even ability to reprogram our ARM processors without a disassembling machine. Same goes to the Altera Max 10. So idea is, again, I'm getting pulses from the Ethernet smooth stepper. I have encoders that are looking at the correct position, and it will be running PID loops to compensate for any variation, for any backlash in my system. So if for example, this screw is not precise, that doesn't care, because the precision comes from the encoder and not from these screws. These screws just have to provide at least correct direction if we rotate, and if it's correct, it will be able to stabilize. So yeah, this is my project. It's getting a bit, as you can see, out of the control. I still have to design for pure sinus driver for this motor, and of course, because I have ARM Cortex M4 processor, or I will use even a higher class processor, I can basically write have correct profile of this motor with all its imperfections and map it to the encoder. And of course, I can make other modification to my sinus table to include to reduce cogging, because basically what I have to do is put huge mass on this motor, so cogging is not affected, cogging is not coming into the play, and turn this motor very fast and write back EMF waveform, and from that generate a capture compare table, or basically a sinus table for each axis individually, and map it to the encoder. It's not difficult, but it can reduce vibrations and so on, because this is a monster. This is a monster, not a motor. From the drivers I have, it even can't move. I was barely I was just was barely spinning with my highest power BLDC driver that I have. So that's, and a drive will be made from the it will be from 3-phase or 2-phase, and I will have a free basically free phase shifted controllers with synchronous amplification that will be running in producing sinus wave, and for each full bridge I will have silicon carbide MOSFETs, and for synchronous rectification I will use something very beefy, or I will use gallium nitride. I still don't know. And I like this because if I basically turn off, if I see that there is too much current draw or something that is going going south, basically I will shut down synchronous rectification. This motor will go into the high Z. Driver that providing the power is go to this high Z mode, so there is no, so motor can run freely. Yeah, so this project is quite nice. I'm very eager to do first cuts with this machine because it should be very good and very powerful and should last with the parts I have forever, at least for my usage. If I make a business out of this machine, yeah, it will be used up much faster. But the parts I have, they are top quality, and there is no cutting corners right now, because when I have encoders with 1 micron, I can't do anything stupid. And I will do trust me on this one. So thank you for watching. If you have any questions, I will happily answer for you. And if you know where to find GT2 power grip pulleys at 75 and 48 teeth, I will be very grateful, because so far I wasn't able to find it, and should be at least 20 millimeters wide, or 25. So this is the only part I'm missing, except for spindle. But spindle, yeah, it will be the project on its own. So again, thank you for watching and have a good time.